So let's resume our proof of the third part of the inverse function theorem. Well, the part which asserts that the local inverse is also C1. So let's quickly recall where we were at. So we had f from E to Rn, and we had these neighborhoods U and V, open sets U and V. So this U had the first of all, this A naught. The point that we started with, A naught, is in U and its image is in V, and U and V are open. V equals f of U, and f restricted to U is 1 to 1. This was what we had proved so far, and then the point is, how did we get hold of this U? Well, U was actually just an open ball. So if you go back to see, it's not quite an open ball. We had the defining property of U was f prime x minus norm of f prime x minus a less than lambda for all x in U, where a equals f prime a naught. And lambda was 1 over 2 times norm of A inverse. So this this property, this thing here, is going to play a crucial role now, because so what we are trying to do in the third step is we are trying to show that the inverse function is C1. Now, to show that the inverse function is C1, or to begin with, just differentiable, we need to have a candidate for its derivative, and we know what the candidate is. It's just the inverse of the derivative of f itself. But obviously that assumes that the derivative of f is invertible in an open set. All we know to begin with, we just know that the derivative of f is invertible at A naught, which is this capital A. We know this thing is invertible. If you knew that derivative is invertible in an open set, then the inverse of the derivative will be our candidate for the derivative of f inverse. So let's first do a small linear algebra lemma, and that's where this is, So what this is, this neighborhood U has been chosen so that the derivative at any x, derivative of f at any x is close in the operator norm. to the derivative at A naught. So the hope is that since we know A is invertible, since f prime is close to A, we would want to say that f prime x is invertible as well. And then we will be able to take its inverse and prove the differentiability of G, which is f inverse. So let's do a small linear algebra lemma first. It says that if two linear transformations or matrices are close, then if one of them is invertible, the other one is as well. Let A be an invertible linear transformation of Rn. If norm of B minus A is less than 1 over norm of A inverse, then B is invertible. So here B is any arbitrary linear transformation of linear operator of Rn. So B is LRn. The set omega, usually this is denoted by GL and R, but Rudin uses this notation capital omega. The set omega of invertible linear transformations of Rn is an open subset of all linear transformations, and we can define a map from omega to omega from an invertible linear the set of invertible linear transformations back to itself by just taking the inverse. This map is continuous. Now this is a very basic and useful fact, not difficult to prove, but it something which occurs in various places. The observation that in the set of all linear transformations, which is a vector space, the vector space of all linear transformations, the set of invertible linear transformations is an open set. Now there are many ways to see this. For example, one quick way, which is not the way which Rudin does it, is to work with matrices and then square matrices. Then the set of linear transformations would be this invertible linear transformations would be those with determinant non-zero. So essentially, if one can prove that the determinant function is a continuous function on the set of all matrices, which is quite simple thing to check, and then it will follow that determinant inverse, the inverse image of the open interval 0 infinity and minus infinity 0 is precisely omega, and therefore it would be open as well. That's one way to go about it, but it uses determinants. Here's a more and moreover, here the advantage is that we are not just saying it's talking about openness and so on. We are giving a ball of a specific size. See, if A is a point inside omega, we are saying that anything whose distance from A is less than this very specific quantity is also in omega. So this is quite useful. It's not just that it open. We know balls of specific sizes are contained in that. So let alpha equals 1 over norm A inverse and beta equals norm B minus A. So the assumption is that then beta less than alpha by assumption. We would like to show that B is invertible as well. So let's show that in fact that the kernel of B is empty. So it's enough to we will show kernel of B is a trivial subspace, i.e. B is 1 to 1. Since we are working with linear transformations from Rn back to itself, 1 to 1 is the same thing as onto. Therefore, B is bijective, which is the same thing as saying B is invertible. So let's show that the kernel of B is 0. So I want to show that Bx cannot be 0 for any x. So let's take x in Rn. And let's start with alpha. Alpha was this 1 over norm A inverse. Alpha x equal to alpha A inverse Ax, which is less than or equal to, as usual, A inverse Ax so alpha was 1 over norm A inverse, so this thing cancels out, so this is equal to norm Ax. So norm Ax will be greater than or equal to alpha times norm x. Well, where were we? Yeah. So, right. So then, but actually I'm interested in B. So I'll just add and subtract B here. less than or equal to norm A minus B x plus norm Bx. And this was B minus Ax. This was what we had called beta. So norm of this will be less than or equal to norm A minus B. So norm x here plus Bx. So the upshot is that norm Bx will be greater than or equal to alpha minus beta times norm x. And I assume that alpha minus beta is always positive, is not all, it's a constant anyway, it's a positive constant. If x is not equal to 0. So B has the kernel of B is trivial, and therefore B is injective, and it's 1 to 1. Therefore, omega is open. What we have proved is that if we imagine if this is omega, the set of invertible linear transformations, if A is a point inside this, shown that the ball of radius 1 over norm A inverse, this ball is entirely contained in omega. So as I said, the advantage of this proof is one knows that, one has a estimate for the size of the ball contained in omega, which is helpful for what we are going to do. For part B, I would like to show that part A says that if this is open, but now I would like to say that the inversion map, which was let's say x going to x inverse, this is continuous. So I'd like to take 2 points A and B and compare their size of their inverses, norm of the difference of their inverses. So let's do that, which is replace. Remember, we started with this inequality. Yeah, actually we ended with this inequality. What was this was? Let me just write it here. We had norm Bx greater than or equal to alpha minus beta norm x. So let's replace x by beta B inverse y. So now I am assuming that B is also invertible. So then I will get so I'll start with the right hand side, B inverse y, and I had alpha minus B beta less than or equal to norm y. So the operator norm, this holds for all y. So the operator norm of B inverse, let me take this to the other side, less than or equal to alpha minus beta inverse. Now here's a small trick or algebraic identity. We are interested in B inverse minus A inverse. We want to, as I said, we want to estimate the size of this to establish continuity of the inversion map. The small trick is you write it as B inverse A minus B A inverse. And then let's take operator norms. B inverse minus A inverse less than or equal to norm of B inverse, norm of A minus B. The main thing is this A minus B here. And we now can control all of these things. Norm of B inverse, we just established that here alpha minus beta inverse. This we can in fact leave it as it is. And what about this one? Well, norm of A inverse is by definition alpha, 1 over alpha. So what we have is B inverse minus, I just write the same thing again, is less than or equal to beta inverse norm of A minus B alpha inverse. And remember, this alpha was just dependent on A and beta was in fact I can put actually not quite this was alpha minus beta inverse, alpha minus beta inverse, and then this. So the upshot is that we are able to control the size of B inverse minus A inverse in terms of B minus A. Therefore, if norm of A minus B goes to 0, i.e. B goes to A, then B inverse minus A inverse also goes to 0. i.e. B inverse goes to A inverse. Right. Well, one has to be, I mean, this in this expression here, alpha just depends on A, but beta depends not just on A. Remember, beta was norm of A minus B. So it depends on B as well. But as B goes to A, this beta goes to 0. In fact, I might have put a beta here as well instead of this. Beta goes to 0, so this whole thing will go to alpha inverse. But main point is that this goes to 0, this expression, the middle one. Therefore, x going to x inverse is continuous. Now let's go back to our proof. So as I said, all this is just to check the differentiability of F inverse. And in my last class, in order to set up the quotient for checking differentiability, I had introduced these things. So let y belong to V. Remember, this was U. So this was G equals F inverse. So y, and then y plus k, x, and then x plus h. So I started with y and k small enough so that y plus k also in V. Since V is open, for k small enough, this we know that this will continue, y plus k will be in V. There exists x with x in U, x plus h in U, with f of x equal to f of x equal to y, f of x plus h equal to y plus k. So this was just the setup for working with the definition of the derivative of F inverse. Now let's, and we had to, at some point, we had to, using this, the auxiliary function phi, we showed that norm h is less than or equal to lambda inverse times norm k. This was a technical point, important technical point. The thing is, when we are going to talk about differentiability of F inverse, we'll start with y and y plus k. Once we have this y and y plus k, just arguing like in this page, we get hold of x and x plus h. Of course, y is fixed, so x is going to be fixed as well. But the point is, this k is just some vector small enough in norm. And the corresponding h that I get here, it's important that I know this expression here does not say anything about how big or small h can be. That requires a separate argument, and that's what we have here, that the unique h that we get for every k, its norm will be less than this. So in particular, what we need is h goes to 0 as k goes to 0. Just the simple thing. Okay, this is what we had last time, and today we proved that invertibility is continuous, etc. Now let's go back to the definition of the open set U. That's how I began today's class. Since norm of f prime x minus a less than 1 over 2 norm A inverse, this was what we had called lambda, for all x in U, Of course, the way we chose this right hand side is one already assumes that one knows this lemma. See, this lemma which said that, where were we? Oops, it's quite a while back. Right. Yeah, this one knows that if b minus a is less than this quantity 1 over norm A inverse, then b is invertible. This is the very basic linear algebra lemma. Keeping this in mind, in fact, the proof of the inverse function theorem starts with keeping that in mind. Because that's how we got hold of the very first step was getting hold of the set, open set U, and that was defined by this same inequality. We have an extra 2 here, which was added for a different reason. Even if we didn't have 2, the 2 was added to get the contraction mapping property, but if we didn't have 2, still we would be able to say f prime x is invertible. By the lemma we know that f prime x is invertible. So this is what I said in the lecture, that open set U that we had chosen was such that it will guarantee that any x in that open set, the derivative still continues to be invertible. Once we have that, now we have fixed x anyway. So now we have fixed y and x. Let t equals f prime x, the derivative, and its inverse. Then it becomes a straightforward matter. So we just have to, so this is our candidate. The main observation is that this is our candidate for the derivative of g equal to f inverse at y. So as I said, this is our candidate. So we actually have to check that this indeed satisfies the definition of the derivative. So let's do that. G of y plus k minus g of y minus t of k. What I would like to show is norm of this divided by norm of k should go to 0. Then I would be done. So let's write this out. G of y plus k, well, these are the two things that we had. So I can write x equals g of y, taking inverses, x plus h equal to f inverse y plus k, which is g of y plus k. So this would be g of y plus k. So this was x and this was x plus h minus tk. So this is just h minus tk. And so I can now h is, I want to write this. The idea is to basically write it in terms of everything in terms of f. and then use the fact that f is differentiable. So how would I write everything in terms of, so this h, for instance, I'll write as t f prime x h. Remember that t is just f prime inverse. So this is just the identity t times f. And this second one I'll write as t time t of k. Well, what was k? K was f of x plus h minus f of x. Right, so because what we had was f of x plus h equals y plus k, and f of x equals y. So the difference between these two will give me k. So t of something, so t of, so I'll put a minus sign here, minus f of x plus h minus f of x minus f prime xh, which is good because the right side is exactly the numerator of the difference quotient for f. Now divide both sides by norm k. Then I'll get g of y plus k minus g of y minus tk divided by norm k, and take norms. Norm of this equal to well, less than or equal to norm t, norm of f of x plus h minus f of x minus f prime xh divided by norm k. Now we'll use that for something we had proved last time, that norm k, this is where I need that. I need a relation between norm k and norm h. So norm k was greater than or equal to, remember what did we have? Yeah, norm k greater than or equal to lambda h. This implies this, whatever this we have here, so 1 over norm k will be less than something, so less than lambda times f of x plus h, oops, I ran out of space here, implies RHS less than or equal to norm t over lambda f of x plus h minus f of x minus f prime xh by norm x by norm h. As k goes to 0, h goes to 0, therefore RHS will go to 0. Therefore, G is differentiable at y, and G prime is equal to exactly that, what we had started with, T. G prime at y equal to T equal to f prime at x inverse. That's it. So directly from the definition, we have proved that it's differentiable. Now, what about, yeah, which in fact I can write as f prime g of y, x is g of y, inverse. So g is differentiable on the open set V. What about the continuity of the derivative? Now, if you look at the derivative of g, it's a composition of various things. One is y going to g of y. The other one is x going to f prime x. And the third one is x going to x inverse. Composition of three maps. G prime is a composition of these maps. This is from Rn to Rn, the first one. Second one is also from Rn to Rn. And the third one is from Rn to this, well, not Rn, some open set, to the space of invertible linear. The third one is from invertible linear transformations to invertible linear transformations. The second one is from open set to the space of linear transformations. So all these are continuous. We proved that the last one is continuous of these. So here I should say continuous maps. The last one is continuous, is the linear algebra stuff that we discussed earlier in this lecture. The second one is continuous because f is C1. The first one is continuous because g is differentiable, therefore it's continuous. So we are done. So therefore, g prime is continuous. This proves the whole thing in all its, all the gory details. So in the next lecture, we'll talk a bit about consequences and so on. So I'll end this lecture now.